All right, we are back. Let's get going with our third session of this second day of the ISS Research and Development Conference virtual technical sessions. For those of you coming back, welcome back. For those of you just joining, I'm Jim Way. I'm Executive Director of the American Astronautical Society. We host these technical sessions in partnership with the ISS National Labs, have for many years, and we'll see if we do this again sometime in the near future. So what we'll do is we'll get going with these presentations, and our chair for this afternoon is George Fries. He is founder of Supernal Technical Innovations, LLC. So George, I will turn it over to you.
Thanks a lot, Jim. Um, so with these virtual technical sessions, what we'll do is we'll present the first 5-minute executive summary. Then we'll open up for questions for that author. We'll then move to the next presentation and author and so forth. So after each presentation, we'll have that author come on the screen and begin the Q&A from anyone that wishes to ask a question. But the webinar attendees will not be able to come on screen, so please use the Q&A tool to submit any questions you might have. So if we have time left at the end of the session, we can address any additional questions that might come along. And just be mindful that there are full 20-minute presentations available online. I think Jim has dropped the link in the chat there. So let's get started with the first presentation. Okay.
Emily's gonna, oh, we've got it. Okay.
Hello, I'm Naohiro Sato from JAMS. It is my great pleasure to present JAMS initiatives of LEO commercialization in Heaven 1 at this webinar. JAMS has been supporting JAXA for GEM development, operations, and utilization since established. To prepare for the commercial space station era, JAMS is now a partner for vast commercial space station, Heaven 1. We will accommodate our own payload in Heaven 1 to conduct commercial business. It will be a trial of several business models in preparation for LEO commercialization. This is overview of JAMS payload. It is single mid-deck locker equivalent size. It can accommodate 1U unit size sub-payloads of customers inside to promote various utilization. It can also accommodate memorial items to launch to space. Our service name is Kurabox. Kura is Japanese, and it means a traditional storehouse in Japan that stores valuable items. Kurabox now offers two types of services. Kurabox Express, transporting customers' goods to space and back. Kurabox Lab, customer payloads of 1U unit is located inside for experiment with power and data connectivity. Customers can design their payloads for themselves. JAMS also plans to offer the base plate for sub-payloads to make the interface coordination and interface verification simple. Opportunity of JAMS mission in Heaven 1 is important for our business model trial. When we access to researchers for space mission, many of them have high motivation to do it, but budget is always a problem for them. In the last Kirara, we had Hungarian researcher who had an idea of a space experiment. Fortunately, right after Kirara mission in SpaceX CRS-32, a Hungarian astronaut planned to go to the ISS in the private astronaut mission of Action 4, and FUNO supported it. So we introduced the Hungarian researcher to FUNO to support her mission, and FUNO agreed it. Her samples finally located in Kirala for experiment in space. In this way, we would like to test a mechanism for matching researchers with sponsors in space missions. It is our challenge how to make space missions to be attractive for sponsors. In Kirala, mission label with FUNO logo was attached on the cube for photo shooting. These are just ideas that we have now. James think business model innovation is necessary to promote real commercial utilization. Again, James' mission opportunity on Heaven 1 is challenging, but it is one for which we should be grateful and exciting. For further information, please access to James service guide. Your participation in our challenges is most welcome. Thank you for your attention.
Thank you so much for presenting your fine research here. While we're waiting for some questions to come in, I have a question. This will be on the Haven 1. When is it supposed to fly?
Thank you very much for this opportunity of the webinar. Yeah, it is officially said that it will be next to May, so May in 2026.
Oh, good. And so it will have a permanent berth on Haven 1?
Pardon? Sorry, I missed the question.
Will it be permanently installed in Haven 1?
Yeah, it will be installed in Heaven 1 when launch. Yeah.
Yes. Okay, so we have a question here. What role is JAM seeking to play in the CLD era?
Yeah, that's a very good question. That we always say that we would like to be a kind of total service provider. We'd like to provide our service using our own assets, like CloudBox. And we also like to provide the services using other CSP's facilities. We already did it in the ISS. So anyway, we'd like to do some service to be a service provider using the all infrastructures in the CLD. That is our position in the ISS, in the CLD area. So.
Okay, thank you for that answer. The next one, can this work when there's no crew on Haven platform?
Yeah, that is one condition because we had that the Heaven 1 crew stay is limited, not for long like the ISS. And yeah, of course, that can be remotely controlled. So there we can do the mission without astronauts on board.
Excellent, thank you. How much power can you supply?
Yeah, good question. I don't know. Sorry, I don't know if it is already in public, but it's not much. Yeah, it's power supply is limited. Sorry, I need to check if it's already in public yet.
Okay. Let's see. Don't have any other questions at this point. Could you give a general overview of the services that the payload can provide as far as the various interfaces?
Yeah, sorry, is it question? Could you repeat the question again?
Yes. Could you provide a overview of the services provided by the payload?
Yeah. So, yeah, our service payload is like, as I mentioned, that each one is a box express that is for the launch to the customers' goods, uh, and the other is uh, ClearBox cube, ClearBox simple experiment using one unit cubes. So customer don't need to can launch any items if it is the envelope is satisfied. Satisfied. So our service is very flexible. We can do the experiment for the maybe like bioscience things or material things, or even we can do some advertising items to be launched.
Okay, thank you. So we're limited to 10 minutes. How are we doing, Jim?
Just fine. If there's no more questions, yeah, we should move on.
Okay,
Excellent.
thank you so much.
Thank you very much.
Thank you very much.
Good luck with your payload. Yeah, the next one is space
In this
shower.
presentation,
Um,
I will introduce our collaborative research of two
Hang on.
companies, Japan.
Okay. Go ahead, Emily. Thank you.
In this presentation, I will introduce our collaborative research of two companies, Japan Manned Space Systems and Science Co. Ltd., to develop Space Shower. My name is Megumi Wada, a project member from Japan Manned Space Systems, or JAMS. This project started just last year, but we are already seeing progress. As part of the space community, we've always known that there is a demand for a shower in space. However, there are several major difficulties, and therefore a space shower has never been realized in a practical manner. I will talk about these challenges and how we plan to overcome them. This is what we would like to achieve ultimately. As the commercial space industry is expanding today, more and more people are going to space, looking forward to an experience of a lifetime. But what if you cannot take a shower while you are in space? Today, astronauts can clean themselves with towels, hot water, liquid soap, rinse shampoo, so they can clean themselves. However, astronauts need to exercise 2 hours a day, and change of clothes are not abundantly available in space. Therefore, we believe there exists a need for a shower in space, but there has not been a realistic solution yet. Before discussing our research, let me introduce a little about who we are. The first company, JAMS, specializes in operation of the Japanese module of the ISS, called GEM or Kibo module. We have been involved in all aspects of Kibo operations. Some of us are flight controllers, some of us are instructors who train astronauts or flight controllers, and some of us monitor the health of Japanese astronauts. JAMS contributes to this research as an experienced key player in Japanese human spaceflight program. The other company is Science, a Japanese manufacturer company specialized in highly innovative technology called fine bubbles. Fine bubbles are extremely small bubbles. When mixed with water, these fine bubbles increase the washing power while using less water. Science brings technology, which is the new way to answer the unique demands of the space environment. In building a shower in space, there are several challenges to overcome. First, we need to save water. Water is a very limited and critical resource in a spacecraft. Second, we need to ensure user safety. For example, we must avoid the risk of shock hazards where electricity is used or suffocation from the water since water behaves differently in space. Third, we need to contain water. This is to prevent the water to cause damage to the system. Fourth, we need to save astronauts time by minimizing maintenance. Finally, we need to save money. Taking into account all of these points requires a lot of effort. We need to balance out all the considerations and achieve cost efficiency. And this is how we tackle these difficulties. First, in order to save water, we utilize the fine bubble technology and recycle the water within the system. Second, we will contain the water in a closed system. This allows us to control the water flow and capture water after going over the body. Third, we limit the maintenance need in this design concept. Finally, we start with a small-scale product so that we can assess the feasibility of the design step by step. We have a small-scale design concept which we call Mark I Alpha model. We are currently working on a prototype, and this model is expected to be tested on orbit as early as 2027. There is another small-scale model, which is called Mark I Bravo. The final model we aim to build upon these smaller models is Mark II, the capsule-style shower. Our belief is that the space shower can contribute to not only LEO space industry, but also for the coming lunar and Mars exploration and spin-off applications on Earth, such as nursing care and evacuation sites. Before I finish, I have 3 questions for you. If you are to go to space, how important is it to have a shower in space? If you are a commercial space station owner, how would you take care of the QoL aspect of the spaceflight experience you are offering? And finally, what is the absolute best spaceflight experience you can dream of? I look forward to hearing from you at the Q&A session. Thank you for watching and see you soon.
Welcome and thank you for presenting your research. It's very fascinating.
Thank you.
We have some questions here. And I think the answer to your question, if I'm going to space, I really would want to be able to take a shower. Yeah. So the first question is, would this be a pod with water recycling capabilities? Isn't this like suited for space tourism? And I think that's one of the things you touched on, right?
Yeah. If I may add a little bit on that. Yes, that is a capital style shower you're aiming for ultimately, but as I explained in the presentation, we are still in the development of prototype of a rather smaller scale model. Yes, what we are aiming for is that this shower be used for both space tourism purposes and also for governmental um, missions, like, oh, we are going back to the moon and possibly on the Mars in the near future. So hopefully our product will be useful in that occasions as well.
Yes. And someone asked, are these small bubbles or is it steam?
Yeah, the current prototype we are developing utilizes water, but this fine bubble technology utilizes like very small bubbles mixed with water, so that way it's very effective. So that's what we're using.
Okay, so you don't turn the water into steam, you infuse it with bubbles. Something like that.
Yeah, that's not what we are thinking right now. We cannot rule out any possibilities, and we are still in development. So we are not entirely like going to say we are not absolutely not going to use a steam or anything. But if you want to have a steamy kind of capsule, then probably we might develop it in the future. But yeah.
Okay, someone said, great presentation. I would want a shower too. Are you planning in the future to make a similar clothes washer?
Clothes washer. Yeah, that is a very interesting possibility, and I think our research may um, lead into that kind of applications. I think there's definitely a possibility.
Here's another question. How would you make money from your product? Would you charge by the shower?
Yes. Of course, we want to commercialize the shower. We hope it's going to be successful because we believe this space shower will be a role model product of like a space company and non-space company partnership, going like entering into space industry and developing a new kind of solution to the challenges and quality of life in space. So we see it as a business project, and what we are envisioning right now is like probably commercial space station might want to purchase it and install it on their stations, or maybe we can lease the product depending on what they want or what we want. And but we are very much open to, well, how the contract might look like. So I mean, if there's anybody who want to discuss it, we are very much open to proposals and contacts. So it would be great if anybody wants to um, talk to us about it. We are open to, we are very flexible on that.
Okay, thank you. So someone's asking, have you taken some lessons learned from the shower that was in Skylab?
Yes. Actually, in the longer version presentation, I discussed a little bit about the Skylab and then Russian Mir station shower. Yes, we've taken lessons from it. They they were like very interesting attempts to build a use a showering space, but ultimately they didn't carry on to today because it was so bulky and took such a long time to um, yeah, use it. So we try it, make it a bit more user friendly. Um, so yeah, definitely lessons taken from history.
Someone pointed out that Tide, the company that makes the washing powder, is working on space detergent and a washer, I think. I'm not certain about the washer, but I know I've heard about space detergent. Maybe something
Space
you want to look at.
detergent.
Yeah.
Yeah, probably. Yeah, we haven't. Yeah, I wasn't aware of that project. Thanks for pointing out. Maybe we can work together in the future, or I'm not sure about. Yeah, definitely. Um, yeah, point taken, I think. Yeah, it seems like a very interesting project. Hopefully we'll have an opportunity to look into that.
Someone asked
George,
whether you could use this to wash clothes, and I think you've already answered that one.
Yep.
That's something you're going to look at, and then so this is a pod that people get into to take a shower. It's self-contained, so that the water is contained within this module. So I don't know. I think that's all the questions we have right now.
Excellent. Thank you for your presentation.
Oh, hold on. There's
so
one
much.
more.
One more.
Oh.
Yeah.
Oh.
So will you be recycling and filtering any gray water from the machinery, greenhouse projects, heating, and AC to use for the shower? And I recall you did cover that in your presentation, right? That it's going to be recycled.
Yeah. Yeah, I believe so. Yeah, thank you for that question, though.
Yes. Okay.
Thanks again.
Thank you so much.
Go ahead with the next presentation, please.
Welcome to the technical session titled Enabling Commercial R&D Project in Microgravity. ESA BSGN Industry Accelerator Initiative. I'm Francesco Liucci, Innovation Manager working at the European Space Agency. The Business in Space Growth Network, BSGN, is an ESA initiative driving commercial use of space to create impactful solutions for Earth and future human and robotic exploration. It comprises of 4 industry accelerators, 3 of which are focused on supporting commercial demand for R&D in low Earth orbit. Each one of them is focused on a different market segment: agriculture and food, life sciences, which include pharmaceutical, biotech, and cosmetics, advanced material and space manufacturing, and the 4th one, which is instead focused on supporting commercial solutions for lunar space resources. BSGN is a catalyst for new markets and ecosystem in space, linking terrestrial industry with space-based opportunities. Some information on the model adopted by the BSGN industry accelerators. These initiatives support industry-driven projects from pre-market stage to beyond. ESA is working with partners that run the day-to-day operation of the accelerators. MEDES, based in France, for the Life Science Accelerator, and the Satellite Applications Catapult for the accelerator focused on advanced materials and space manufacturing. The model adopted established a balance between the incentives provided by ESA and the commitment that is requested by private players. This initiative provides up to 50% of co-funding to support the implementation plan, meaning the project to execute R&D enabled by microgravity, and acceleration services provided by the managing partners, MEDES and Catapult. The industry projects need to match the co-funding provided by ESA and present a technically and commercially viable plan in order to execute the targeted R&D commercial experiment in space. During phase 1, the BSGN Industry Accelerator supported 9 commercial projects featuring startups, SMEs, as well as large entities and academic partners. 5 were supported in the area of life sciences, 2 in advanced material and space manufacturing, and 2 additional projects in agri-food. The current status is that 4 projects have flown already on the ISS in 2025, and 5 are set to fly between 2026 and 2027. BSGN is currently in phase 2. There are new goals open to commercially led projects seeking to do new experiment in microgravity. The current slides provide some insights on the potential next batch for the Life Science Accelerator. There is quite a wide variety of areas that are explored, all of them seeking to address problems, diseases, and conditions that are affecting hundreds of millions of patients globally and underpinning healthcare markets valued in hundreds of billions of euros. The new portfolio of projects proposing experiments enabled by microgravity are not only targeting terrestrial challenges, but they're also proposing solutions that can enhance deep space exploration capabilities. Areas such as on-demand biomanufacturing, smart health monitoring, human tissue and organoids models, new treatment, protective biomaterials and devices, and enabling tech. The BSGN initiative aims to increase the number of projects supported in Europe that can benefit from accessing microgravity conditions. And in order to do so, it aims also to expand its international network in the emerging LEO commercial landscape. 3 are the areas of interest: seeking international partners to collaborate with European entities in commercial R&D areas of common interest, establish challenge-driven initiative, open innovation initiative with large international cooperation in the targeted markets, and increase awareness of the benefit in microgravity by a joint event and workshops. If you're interested, please get in touch with the European Space Agency or one of our partners, MEDES and the Satellite Applications Catapult. Visit the BSGN website for more information. Thank you for your attention.
Thank you so much for your presentation about this project. We have a question here. In addition to ISS, on what platforms can the BSGN portfolio projects fly?
So literally any that are European based and that they are available to fly the design and payload. So at this stage, we are really trying to matchmake the terrestrial customers with new space providers. So we are engaging with free flyers and capsules that are proposing new solution, and some of them will come live starting in 2026, really.
So are you targeting just European entities now, or?
Yes, I mean, it's a European Space Agency funded initiative. So our aim is to support entities that are based in any of the ESA member states. But as mentioned in the last slide, we are looking for international collaboration, and often, especially when we work with large corporates, they are international by nature. And at this stage, if there is any non-European entity that is interested in collaborating with us in any of the area that I mentioned, in any of the markets that we're focusing on, we are pretty happy to engage and start collaborating.
Thank you. Jim, you have something?
Yeah, can you just expand a little bit on your evaluation criteria? It seems like you have a lot of people, looking to get into this, and how do you select them?
So we're trying to establish a balanced view between technical viability of the experiment proposed, including how far they went into engaging with actual commercial service providers in space. So that if the project proposed understand what it takes to get ready to go in microgravity, which are the requirements, how feasible it is, what they want to do, especially if they start from an experiment and a setup in terrestrial ground, and trying to keep a balance also with the commercial perspective. So we do ask to understand how much the research that is intended to be done in microgravity is linked with the commercial outcome. How long they think it will take to have a commercial benefit, including if they can already think in that perspective, how many flights, how many more microgravity experiments do they think they need to get to that level. So we try always to keep a balance between these two main areas. And then, of course, we have a sort of third element, which is the programmatic alignment, especially when we have proposals where solutions are not for terrestrial markets, but they can benefit our space capabilities. We also have an interest in understanding if the agency would like to pursue or be engaged with a particular type of experiment, because it can extend deep space exploration capabilities in general.
Very good. Thank you. George.
I see no more questions. Jim,
Yeah, I
I
think
think we need to move on. Yeah.
Yeah, I think we need to move on.
Okay.
Thank you so much.
Yes, thank you very much.
Thank you for the opportunity.
Absolutely.
Yeah.
Hello, I'm Kazuya Kanai. Today, I'll share the latest update about Japanese key players and their activities for the post-ISS era. Let me introduce my company at first. Japan Manned Space Systems Corporation, or JAMS, has been played by the role in supporting operation and utilization of the Japanese experiment module keyboard on the ISS. Next, I'll give you a brief overview of the current global trends. In the US, NASA has been led in commercial activities in LEO, with half of NASA's resources has been open to private companies and the CLD program moving forward. This is a good model for many countries, including Japan. Russia, China, and India are also advancing their own human spaceflight programs. Notably, China and India have already achieved world-first successes with their lunar exploration missions. Now, let's start main topic. The first key player is the government of Japan. Japan's space policy is determined in the Space Development Strategy Headquarters, which was established in the cabinet. And there are several ministries involved in space utilization, especially the Ministry of Education, Culture, Sports, Science and Technology, and its agency, JAXA, plays a central role in the ISS Kibo usage. This is a new framework image to shift from government-led style to more private sector-driven approach. Private companies will be able to contract directly with Japanese service providers to access LEO. JAXA's function is to support the private companies and procure service from providers as a customer. Now, I'd like to introduce new players who will take a leading role in the future. According to a study we commissioned from the think tank, the space market is expected to grow tenfold over the 20 years from 2020. However, the commercial usage of Kibo by Japanese private companies is still quite limited. We have many challenges to expand commercial utilization of LEO from Japan. JAMS has reached to an answer that Japan's national laboratory is necessary, and finally launched a consortium, Solaxio. This is the next key player. And JAMS itself is also one of the important players. We are conducting various researches and development initiatives to create new space businesses. At the last of today, I'll show you the joint research of the space shower that I'm joining. This is a shower developed by a Japanese private company named Science Co. Limited. Simply apply the shower containing a lot of fine bubbles and gently rub. It can remove oil-based markers. My challenge explores whether such innovative technology could be taken into space. I mean, even if you finally get to go on that space trip you've always wanted, wouldn't it be awful if you couldn't take a shower? Please share your thought with us. Thank you. Thank you for listening.
Thank you for sharing your presentation. It was very informative. So let's see. Are there any plans to move scientific or commercial facilities on GEM to a commercial space station like Axiom?
Well, thank you for the question. I think there is possibility to transfer our payload to commercial module to such as Axiom. But at this point, it is not determined yet.
Yes, I understand. So we have another question. Do you think that the shower could be part of an experience, perhaps an environment that also grows plants or other physiological support? So,
Yes, thank you for the question. Yes, the shower containing fine bubble have a lot of potential. So yeah, it can be applied to good experience in space travel. Also, it is good for treating plants, fish, growing fish, and while we can treat gently the injured area on our surfaces gently. And yes, it is also good for psychological support in space, even in ground too, as well.
so one question I have, do you think Japan may jump in and create its own space station?
Yes, one company is chosen to develop Japanese original space module, but it is little bit for future. Maybe U.S. commercial station is earlier than us.
Okay. So let's see. Someone had asked, do you have any plans to work with the Chinese or maybe put your shower in their space station?
Sorry, I couldn't catch. Could you say again?
Someone had asked, are you planning maybe to work with the Chinese and put the shower or sell the shower to the Chinese?
On Chinese space station. If they would contact to us, yes, we are welcome to serve our shower to China. Yes.
Okay. I think we're out of questions, out of time.
That's very good.
Thank you very
Thank
much
you very
for
much.
Thank
spending
you.
your time coming here. Thank you.
Okay. I think we're ready for the next one.
Hello, my name is Erica Wagner, and I'm excited to be talking to you today about the exploration company's Mission Possible flight that flew in the summer of 2025. Reusability has been transforming the modern space economy, yet orbital capsules remain a relatively underdeveloped capability. Mission Possible marked an important step towards advancing these reusable capabilities, opening the market to all sorts of different uses in science, technology maturation, education, the arts, and beyond. Founded in 2021, the exploration company is growing fast, with locations in Europe, the US, and the UAE. With more than $200 million in venture funding, more than $800 million in contracts won with customers, this is a company that is poised to change the way that we think about the affordability, availability, and sustainability of space. In the last 2 years, we have launched 2 orbital missions. Mission Bikini at just 30 kilograms, starting to demonstrate the capabilities of the reentry systems. And then Mission Possible, a 2.5-meter capsule capable of carrying up to 300 kilograms of payload, launched in the summer of 2025. We'll be talking more about that today. Both of these are technology demonstrators set up to mature the capabilities we need for our Nix Earth spacecraft, a 4-meter capsule, 13 metric tons, capable of taking multiple metric tons up to low Earth orbit and back down. Come learn more about the 7 phases of the Mission Possible ConOps, the ways in which we were thinking about de-risking this hardware step by step in service of the future Nix architecture, and the results from our mission in June 2025. More than 24 payload customers from around the world used Mission Possible to explore the impacts of microgravity on their systems, to learn more about their technologies, to teach students about the power of spaceflight. With a successful launch on the SpaceX Transporter 14 mission, activation of the payloads, separation from the launch vehicle, re-entry back through Earth's atmosphere, and establishing of communications, Mission Possible marked a fantastic opportunity for the exploration company to learn. We'll talk about all of this, as well as how to join our teams around the world in our presentation at this year's ISSRDC. Thank you so much.
Thank you for your presentation. There are so many great accomplishments that you have made. Very much to be proud of there.
Thanks, George.
Yes. So let's see. We don't have any questions coming in.
I got a quick one while we're waiting for others to post. Sure. You talked about affordability. Can you actually put some numbers on that as far or comparison's sake? How affordable is affordable?
It depends on the mission, right? So
Yeah.
the bigger your capsule gets, the less you pay per kilogram. So we are really, targeting to be competitive with the most affordable vehicles on the market at our largest capabilities. Mission Possible was a development mission that was partly backed by our venture funding, so we were able to bring down those costs to closer to $20,000 per kilogram, which is really quite stunning. And as we move forward into the future, I think that the questions of how this industry purchases space is an interesting, will span a lot of different models. We'll see some that are funded by agencies, some that are procured commercially, and some where you might even see co-investment between platforms and developers, so that people are taking advantage of the upside potential we all win big together.
That's great. Yeah, makes a lot of sense. All right, George, looks like we got a bunch of online ones. Go ahead.
Yes, I was going to ask, what launch platforms have you been using to get to space?
Yeah, so Mission Bikini, our first mission back in 2024, launched on the inaugural flight of the Ariane 6 rocket out of Kourou. The Mission Possible flight in June of this year went up on SpaceX Transporter 14 out of Vandenberg. And we're designing the Nix spacecraft to be compatible with basically all of the heavy lift launch vehicles around the world, because we don't think that users should be constrained by launching from a single location. And we want to have the most negotiating power for bringing down those prices for our customers.
Okay, so this question is, what kind of flight rate do you need to get to a profitable cadence?
The profitability is such an interesting question because it depends on the price of your mission. So we will be building our business models around the flight cadence that we can hit. So that means that we're going to be looking for that sweet spot between the supply and the demand curves. When we look at the LEO market for destinations, so going to the ISS first, we're on ESA's LCRS contract. That's the LEO Cargo Resupply Services, very similar to CRS-2 here in the US. So we're on that contract to provide first flights to the International Space Station and then to the commercial LEO destinations as the European Space Agency needs those. We're also working directly with the commercial LEO destination providers, and we have public contracts with Axiom, Vast, and Starlab to provide cargo services to their stations. And I think that we'll see how many flights they need per year as the demand signals become clearer over time.
Yes. Do you have any plans to land your reentry capsule on the ground as well as in the sea?
It's a great question. The bigger the vehicle gets, the harder it is to do touchdown, especially for a capsule that's reliant on sort of more ballistic reentry. So if we're starting with the ocean. We feel like that's both the safest spot and the most effective spot for us with the early development. If we have customers that really need precision landing and targeted to a tighter landing ellipse on terra firma, that's something we're open to exploring. We haven't heard much demand for it yet.
Mm-hmm. So can you speak on some lessons learned from Mission Possible? Did any downlink happen before the crash?
Yeah, so we're still going through our final work of our independent review board. That report should be coming out soon, so I don't want to get ahead of that team. But I think what we were able to see during the course of the mission and shared on our live broadcast was that we were able to activate all of our payloads. We were able to establish communications with the payload with the capsule, and we lost the vehicle around the time it went transonic and released its parachutes. So that very final descent phase.
Yes, I think you probably answered this next question. What were the main lessons learned from Mission Possible that are informing TEC's next plans?
Well, I think in some ways that's the main lessons that you learn in building and flying any mission are how to build and fly missions. And that's a little bit tautological, but we built a team that now knows how to make our hardware, how to make our heat shields, how to do complex assemblies. We were able to work with more than 24 payload customers and understand better what interfaces they need to see in our NIX capsule. The NIX vehicle itself is going through the design maturation process with both NASA and ESA for our first flight to ISS in 2028. We passed our phase 1 safety review, actually the same week that we flew Mission Possible this summer. So that was a really important milestone for us. And I think what we're seeing is we're trying to mature these things stepwise and mature them together through flight demonstrations, through ground demonstrations, through interactions with the customer and user communities, so that by the time we get to space station, we are ready to rock and roll and serve the community's needs.
Right. Someone would like to know, can this be used for space tourism or have you explored it already?
Yeah, so from this vehicle that we're designing right now is for cargo only, the NIX Earth capsule, and Mission Possible certainly, you would be a very small tourist if you were fitting inside there. But we are looking at the possibility of maturing NIX Cargo into NIX Crew, similar to the way that Dragon Cargo became Dragon Crew later on. And we unveiled a mock-up of some of our early thinking of that at the Paris Air Show this spring. So if you look up Paris Air Show and NIX capsule, you'll see some pictures.
Okay. Well, I think we've reached the end of the questions.
Wonderful. Thank you so much.
That was great, Erica. Thank you so much.
Awesome. Yeah.
And George, do you want me to introduce you? Since you're our last presenter.
Okay.
Go ahead. Off we go with George Fries.
Today we'll explore using centrifugation for artificial gravity. This could mitigate astronaut health risks, help adapt appliances, and lead to safer vehicle designs. Building on early research suggesting astronauts can adapt, presented here are centrifuge concepts to further these critical studies. Why use a centrifuge in microgravity? For three key reasons. First, to investigate mitigation of health risks for astronauts on long missions. Second, to examine the feasibility of adapting terrestrial appliances for space. And third, to better understand design limitations, such as the Coriolis effect and astronaut locomotion. The concept is rooted in Einstein's thought experiment. He theorized that if a chest in space, as seen here, is pulled upwards, the occupant would feel a force indistinguishable from a gravitational field. This creates an equivalent force of acceleration, the core principle of artificial gravity, but it is not a true gravitational field. To clarify, true gravity affects every atom, but artificial gravity is a kinematic force from a spinning body's angular velocity. As the animation shows, an astronaut floating inside the station is not affected. The force is only imparted through direct contact with the rotating structure. On Earth, our vestibular system is tuned to gravity. In orbit, free fall cancels the gravity force. This raises a key question, illustrated by the elevator comparison. How will an adapted vestibular system react to purely kinematic forces like Coriolis? This requires empirical testing. A common misconception is that short-arm centrifuges will cause persistent motion sickness. However, the few existing studies, including Skylab and Neurolab, generally refute this. The key finding is adaptation. Astronauts appear to become less susceptible after 3 to 5 days in orbit. This indicates that ground-based studies alone are insufficient for this research. Looking at the historical data, the Skylab M131 study found only slight adverse effects on orbit after a 6-day adaptation period. On STS-42, initial motion sickness largely subsided by day 3 for most of the crew. And on STS-90 Neurolab, with an even higher RPM, no motion sickness was reported, and the data showed perceptual adaptation. The evidence consistently points towards successful human adaptation. This Skylab data is particularly compelling. The chart shows that while astronauts experience significant malaise pre-flight, the malaise levels in orbit after a 6-day adaptation period were almost zero, even while performing 150 head movements. This provides strong support for the theory of in-orbit adaptation to rotating environments. For practical applications, 2 centrifuges are discussed: a large 3-meter centrifuge for long-term orbital and off-world health mitigation, and a smaller 1.25-meter version for appliance evaluation, design studies, and other human health research. A centrifuge may offer systemic health benefits. It is hypothesized that it could help mitigate cardiovascular and musculoskeletal deconditioning, stimulate the vestibular system in a way similar to Earth's gravity, and potentially reduce the fluid shifts linked to vision issues. As a unified countermeasure, it could challenge multiple body systems simultaneously. Of the very few examples of appliances in orbit, the zero-G kitchen is a representative case. This investigation cooked a cookie in microgravity, where convection heat transfer was absent, and it took much longer than expected. It is hypothesized that a centrifuge may provide the necessary buoyancy and convection for such appliances to function. However, it is not yet known if a centrifuge's kinematic force is a sufficient substitute, prompting a need for further investigation. Regarding vehicle design, the Coriolis force is a major factor. The use of rodent habitats in centrifuges to study its real effects is of interest. This research is crucial for understanding the potential hazards, informing the safest and most effective layouts for future rotating space stations, and observing how organisms adapt their movement. In summary, gaps in our knowledge demand further investigation. A large-scale centrifuge is a critical next step for testing health strategies for the Moon and Mars. A moderate-sized centrifuge will help us study Coriolis effects and the feasibility of adapting appliances, accelerating development for the entire future of space exploration. This concludes our formal presentation. The path forward requires a dedicated and empirical approach to answering these critical questions about human adaptation to artificial gravity and configuring centrifuges for space habitation activities. The technologies we've discussed have the potential to be truly transformative for the future of human space exploration. Thank you for your time and attention.
All right, George. Thank you for that informative presentation.
Yes, thank you.
Yeah, we're looking for some questions from our online attendees. While we're waiting, I got one for you. So you talked about right at the end there, a large scale centrifuge, terrestrial for terrestrial testing, correct?
No, that would be
okay. That was
in orbit in order to check the artificial gravity and the Coriolis. Yeah.
Okay, so can you put into terms what large scale means?
Go ahead. Well, in one of those pictures in there, it showed like a 3 to 4 meter diameter that would fit inside of a node, in the end of a node, and then an astronaut could be inside of that. It's kind of cramped. It's not. You could maybe. One person was saying they'd like a place to go smoke cigars or something and to relax. And so you could maybe get two of those bays out of one of those, where people could go and maybe have a sleep cycle, be able to, if you spend 8 hours in a 1G versus the rest of the time in 0G, does that really help, So Lynn has a question. Is there any thought of working with both commercial and international partners to chip in and build a test system? Well, that's a thought. That's a very good thought. Thank you for that suggestion. George, do you prefer large rotating structures to be rigid, or can they be tethers? Well, the thrust of this presentation is that there's been no studies that actually had humans in the loop, aside from those with the Skylab and 2 of the shuttle flights that actually had humans inside of rotating, and they were not. One of them is classed as centrifuge. It's only a 2-foot radius arm. So, but if you look at those, the way they're designed, they look like amusement rides, but they're designed specifically to trigger your vestibular function, and it didn't do it, not sufficiently to say that you need a huge rotating structure. So they could be rigid or tethers, but what this is saying is you really don't, short radius is still, based on the data, the hard data, there's no indications that would make us dizzy. What do you believe is the right size and duration for a minimum viable centrifuge to conclusively demonstrate the utility as human countermeasure for long duration spaceflight? Well, the one that Jim was talking about, the 3 to 4 meter, that would be something like what we would need, something that will fit inside the end of a node, which then you could do more extensive real life testing with human beings.
So I got another one for you, George. So you mentioned something about doing it for 8 hours or something like that. So that's a third of your day. Would it be better or worse going from the centrifuge 1G environment for 8 hours, and then you have the remainder of your day in microgravity or 0G, and then you do another 8-hour stint? Does that help, or does it make it worse, like the transition?
Well, the thing is, we don't know, but this realization, the new hypothesis in this paper is that right here, we're sitting on Earth, we have every atom in our body is under the gravitational pull of the Earth, whereas if you're in a centrifuge in orbit, that part is canceled out. The Earth pull is canceled out by the rotation around the Earth. You're in free fall, constant free fall. Right. So therefore, you don't, after you acclimate to that, after 5 to 6 days, you don't have any dizziness or anything like that. So it's hard to tell whether, if you go into a centrifuge for 8 hours, it's all kinematic, it's like foot bone connected to ankle bone connected to shin bone. That's the kind of gravity you're getting. And so there's one more question here, or a couple. Given the idea around artificial gravity having been around for decades, what do you think have been the most significant challenges in creating a stable and controlled rotation for a large-scale artificial gravity station that has not made it possible so far, and what may change in the future? Well, one realization I had is that if you keep saying, okay, you're going to get dizzy if you get into a centrifuge big enough for humans, and so therefore you cannot rotate more than 4 RPM, and it's got to be like 300 feet radius. Nobody's going to build something like that. So we have to kind of bite the bullet and go ahead and build something smaller that we can actually test humans in. Okay, the last question. Mice have been tested in centrifuges. Did we observe useful countermeasure benefits from bone loss and muscle loss? The answer is yes. But those are small, like think of the pumpkin pie at Thanksgiving. You cut a piece out, and that's the space that the mouse is in. They're not really huge, and it's not big enough for vestibular or any locomotion type studies. So you need a little bit larger, 1 to 2 meters would be best for rodent studies.
Okay. I think we're good. So
yes.
Yeah. Well, George, thank you very much. Thanks for
Thank you,
hosting this afternoon's session. And then for everybody left online, we will be doing this all again tomorrow. We're starting bright and early at 9 a.m. We'll do biotechnology and medicine from 9 to 10:10. 10:25, we'll do human health and performance till 11:35. And then 11:50 to 12:30, we'll do fundamental biology. So we're looking forward to those sessions tomorrow. Come on back. And once again, all of this stuff is being recorded. And so we'll get this posted for you as soon as possible and let everybody know. With that,
thanks everyone for attending.
Yep. That concludes the day. Thanks so much, all. Bye-bye.
Bye-bye.